Okay, just now we just derived the magnetic field generated by the long straight wire, and now we make the wire which is like a circular arc, So in this case, we have suppose this is a whole circle. This is a whole circle. So this is a whole circle. So this is a part of the circle. So which is a circular arc, and then the radius of this circle is capital R, and this angle, the central angle is phi in radian, and then we will have B to be mu 0 I phi over 4 pi r, So here we have the current going in this direction, like counterclockwise. So ds will point to this way, and then for this B, it is the magnetic field at the center. It is the magnetic field at the center. Yeah, at the center. So R will be from the arc to the center. So our head point to this way, and of course we know that dB is proportional to ds cross our head. So you use right hand rule, you know that dB, not this point, dB should be pointing out of the page. dB is pointing out of the page, like this one. So no matter which position you are at, maybe you have a ds at this point, and then our head point to this side. Still you have dB point to the same direction, which is out of the page. So when we add all of the dB together, integrate all of the dB together, we have the overall B integration of dB. So similarly, we apply the Biot-Savart law. So we have a mu 0 over 4 pi I ds I theta over r squared. Now r is a constant, so we use a capital R here, and we integrate it from 0 to phi. We assume this is the 0 for the phi, and then this is phi. So in this case, mu 0 4 pi r square I, all of these terms are constant. And and of course sine theta is 90 degree. Sine theta is all 90 degree. So this is 1 as theta is all 90 degree. ds always is always the tangent direction. So it's always perpendicular to r. So sine theta is always 1. So here we have a ds from 0 to phi, which is actually the length of this arc. So this is the length of this arc, which will be, or you can use substitution. So ds is rd phi prime from 0 to phi. So this integration is nothing but r times phi. So one of the R is cancelled. One of the R's is cancelled, and we have phi here. So this is the length of the arc. So it's somehow like integrating a constant. So there is a special case for this equation, which means if we have a full circle, which is usually the case. So if we have a full circle, and if the current is going like counterclockwise, so at the center, the magnetic field will be pointing upward. You can simply use the right hand rule to determine this. You use your forefinger following the direction of the current, and then your thumb will point to the direction of the magnetic field. So now we have a full circle, which means that phi equals 2 pi, which means 360 degrees. So as long as this is 2 pi, so cancel half of the 4 pi, so we have 2R here, and then we still have a mu 0I on the top. So the magnetic field at the center of a loop will be mu 0I over 2 pi. Any questions? Okay, so let's take a look at the sample problem. So now here we have so the wire carrying a current I and consists of a circular arc of radius r, and the central angle is pi over 2 radian, and two straight sections whose extension intersect the center C of the arc. What is the magnetic field B? Thus, current produced at C. So we consider the magnetic field at this point. Okay, of course we can apply the Biot's law, or we can simply apply this 29.9 here. So first of all, for segment 1, we have I here. So suppose we have a ds in this direction, and then R should be in this direction. Or R hat also point to this direction. So as long as for the Biot's law, we have a dB which is proportional to ds cross R hat. So for segment 1, ds and R hat points to the same direction, which means that when they cross together, it will be zero vector. So for part 1, it will contribute nothing. And similar for part 2, ds point to the other side, and then R hat will point to the opposite side, which means that in this case theta is 180 degree. So sine of 180 degree will be 0 also. So in this case, for segment 2, it will not contribute any B field at point Z either. So the only segment will contribute the B field at point C will be the segment 3. So B will be actually you can simply use this one. So mu I phi 4 pi r. So we have mu I phi is pi over 2. This one. And then over 4 pi r. So this is nothing but mu0. Mu0 I, pi and pi will be cancelled, so we have a 8r. 8r at the bottom. So this is the magnitude of the B field. And when we need to determine the direction, of the B field, so actually for this graph, it uses this way. So you use the forefinger, follow the direction of the B field, and then your thumb will point to the direction of the current. So your forefinger follows the magnetic field of the B field, and then this is the current. So this is the current direction. So you can know that this is going into the page. B is into the page. Or you can use the other way. You can use your forefinger. You can use your forefinger. Follow the direction of the eye, and then your thumb will point to the magnetic field direction. It is somehow like hard to draw. You use your forefinger. Follow the direction of the current, because you know the current first. So this is the direction of the current, and then your thumb will point into the page. Actually, draw very bad. Maybe like this. Yeah. Not this way. So this thumb will point to the direction of the B field. So both ways you can find the direction of the B field. Any questions regarding to the direction, because it may be quite complicated to you. And actually, the most difficult part for the magnetic field is to determine the direction. Okay, so if no question, we have another sample problem. So two long parallel wire carrying current I1 and I2 in opposite direction. So what are the magnitude and the direction of the net magnetic field at point P, assuming the following values: I1, I2, and D. So D is the distance between the two wires. I1 is going out of the page, I2 is going into the page. What we concern is the magnetic field at point P. So yeah. So as long as this side is capital R, this side is also capital R, so this angle will be 45 degrees. And you can simply imagine that D is a square root of 2 times capital R. So first we need to determine B1 and B2. So B1 So B1 is going out of the page, and actually it is a long straight wire, So B1 will be nothing but B1 mu 0I over 2 pi out, 2 pi capital out. For long straight wire, of course I1 here, and of course you need to determine the direction of the magnetic field at point P. So you can simply use right hand rule, use your thumb, follow the direction of the I, which is out of the page, and then your finger, which means you use your thumb to follow the direction of the current, and then your forefinger going to this point will be pointing to the top left, So we can get the direction of B1 pointing to the top left. So it is mu 0I, and yeah. So let me just keep it like this. And for B2 is going into the page. It is still a long wire, so it is still mu 0 I2 over 2 pi out. I2. So still you use the right hand rule to determine the direction of B2. So you use your thumb pointing into the page, and at point P, it will point to the top right. So we can get the direction of B2 pointing to the top right. Of course, the magnitude of B1 and B2 are different, because mu 0, 2 pi out are the same. However, I1 and I2 are different. I1 is 15A, I2 is 32A. So B1 and B2 are not the same in magnitude. So you can see B1 is shorter, B2 is longer. So finally, we need to determine what is the total B. Will be B1 plus B2, B1 square plus B2 square, quantity take the square root. Because we can simply imagine that these B1 and B2 are perpendicular to each other. So we can use the Pythagorean theorem to calculate B, which is B1 square plus B2 square, take the square root. So it turns out to be mu 0 over 2 pi out, and then square root of I1 square plus I2 square. So mu is 4 pi times 10 to minus 7, and then so we subtract with 2 pi, we cancel with 2 pi, so we have a 10 times 2 times 10 to minus 7, 2 times 10 to minus 7, and then over R is d over square root of 2, d over square root of 2, because d is a square root of 2 multiplied by capital R. So R will be 0.053 over square root of 2. And then here we have a square root of 15 square plus 32 square. So B will be 180 micro Tesla. And of course, we need to determine the direction of the B field. So as long as this is a right angle triangle, so this is a right angle triangle, so we can simply determine phi. And then we can say that the actual direction would be related to x-axis, and then we can add 45 degrees to it. Then it is the direction of the B field at that point, at point P. So now phi, so this is B1, so this is also B1. So phi is arctangent B1 over B2, which is arctangent 15 over 32, because all the other term will be cancelled. So the only remaining term is the I1 over I2, or maybe I can write it with one more steps. So it is nothing but I1 over I2, which is arctangent. So it is arctangent 15 over 32. So it turns out to be a 25.1 degree. So we may call this one theta. Theta is 45 degree plus phi, which is 45 degree plus 25.1 degree, which is 70.1 degree. So this is 70.1 degree relative to the x-axis counterclockwise. Any questions? Okay, next we talk about the force between two parallel current. So in the previous chapter, we know that if we place a wire in the magnetic field, then there will be Lorentz force acting on the wire. So now if we place two current carrying wire close together, then there will be force acting on each other. And of course, the direction of the force depends on the current direction. So let's see. So it tells you the conclusion first. So parallel wires carrying current in the same direction attract each other, and parallel wire carrying currents in opposite direction repel each other. So the point will be like, so in the previous chapter, we already know that FB from A will be like, or maybe FB, let me see, FA acting on B. Yeah, FA acting on B. FB from A will be like the current on wire B. The current going through wire B, and then L is the length. BA is the B generated by wire A, because in the previous chapter we only know that, we assume there will be a magnetic field there, but in this chapter we already know that as long as we have a long straight wire, it will generate the B field, which means that as long as we place a wire A and then it has IA going from this side to that side, then it will generate the B field at this point pointing downward. You can use the right hand rule to verify this. So BA pointing to the bottom, and as long as the current is perpendicular to BA, which means that there will be a Lorentz force acting on the current and acting on the wire B, due to wire A. So we have FB from A. So this is, you can imagine FBA is like FB, the force acting on wire B from wire A. So we have IB times L times BA, the magnetic field generated by the wire A. So the magnetic field generated by the wire A is nothing but mu0 I over IA over 2 pi R, or D in this case. Here we use D instead of R. So actually this is BA. So we substitute this term back to here. So on the top we have mu0 IA IB L, mu0 L IA IB. And then on the bottom, we have 2 pi D. So overall the forces will be mu0 L IA IB over 2 pi D. And D is the separation between the two wires. IA IB are the currents in the wire. So this is the magnitude of this force. And just now I mentioned that for IA going from this side to that side, so BA pointing downward, and then IB also going in the same direction, so that L point to the right side. So now we have FB is I L cross B. So you can have L cross B pointing to this side, which means pointing to wire A. So here we come up with the conclusion here. As long as the current is in the same direction, then the two wires will attract each other. Actually, due to wire A, FBA point to that side. So likewise, FAB will also point to wire A. So they attract each other. Actually, you can verify by yourself. You can try to draw what is BB, the direction of the magnetic field generated by wire B. What is the direction of BB? And then L should point to the same direction, and then you can finally find that L cross BB will point to this way. So in this case, they attract each other, and if the current are going to opposite direction, if it is IA, it is IB, then in this case, still BA point to the bottom side, however L point to the other way round. So in this case, L cross BA. So this is FBA will point to the opposite side, and so as FAB. So in this case, if the current are going are in opposite directions, then the wire will repel each other. So this is the second conclusion here. And of course, the force will still be like this. The magnitude will still be like this. Any questions? Okay, it summarize again. So the general procedure for finding the force on a current carrying wire is to find the force on a current carrying wire while due to the second current carrying wire. First find the field due to the second wire at the site of the first wire, and then find the force on the first wire due to that field. So similarly, if the two currents were anti-parallel, so it used the term parallel and anti-parallel. Parallel means the current go in the same direction. Anti-parallel means the current are going in opposite direction. Although parallel, when you learn the geometry of parallel, it doesn't have related to the direction. But here, as long as we consider the direction, so this is called parallel, and IAIB. So if IAIB points to the opposite direction, so we call it anti-parallel. So similarly, if two currents were anti-parallel, we could show that the two wires repel each other, and parallel current attract each other, and anti-parallel current repel each other. Okay. So next, this is the most important part in this chapter, which is called the Ampere's law, and of course it is one of the four in the Maxwell equation. So here we need to know another concept, which is called the line integral. Closed line integral. So this is actually a closed line integral. So for Gauss' law, we have a closed surface integral, and when you consider somehow like the current, you still need to do some sort of surface integral. But here we would like to determine the line integral rather than surface integral. So here on the left side it is nothing but a line integral, and on the right side it is like mu0 I enclosed, somehow similar to the Gauss law. For the Gauss law, the left side is a surface integral, closed surface integral, or the Gaussian integral. On the right side it is and on the left side is still multiplied by epsilon naught. So if you still remember the Gauss law, so it is like E dot dA equals Q enclosed. Now we have the line integral on the left side, and then mu0 on the right side, and then I enclosed. Here we have Q enclosed. So usually in the equation related to electrostatic, we will have epsilon naught, and for the corresponding equation for the magnetic field, then usually you replace epsilon naught by 1 over mu naught. So here you can see epsilon naught on the left side and then mu0 on the right side. It is somehow like 1 over mu naught here if you divide mu naught on both sides. So let me simply explain what is the line integral. Let me try. So if we have a path C, which is closed, which means that for the starting point and the end point should be the same, then it is called a closed closed loop, usually denoted by C. And in this textbook, it also call it the ampliance loop. Ampliance loop, like here. It already mentioned here, closed loop or ampliance loop. So in this space, we will of course have a magnetic field. Magnetic field over the whole space, and yeah, this is a closed loop, so that we can divide this loop into many small segments. So it is like ds here, will be a vector, and usually for this loop we will give it a direction. Actually, this direction can be determined by you. So for example, if for this loop we have the direction counterclockwise, and in this case the tangent direction at this point will be the direction of ds. So for every point you will consider maybe b points to design with a magnitude like this. So we will determine for this point we have a b dot ds, and then for other point we have at point r1, and then point r1. Maybe we have an original point here, so this is actually r1. So we have a b of r1 dot ds for this point, and then maybe for the other point we have a b of r2 here. So this is another ds, which is a tangent direction to this curve here. So this point will be like b of r2 dot ds. So we can calculate many b dot ds for the whole loop, and then we add all of them together. We sum all of the b ri dot ds of r. Actually, this also related to the r, because all of the ds are different. So when we add all of them together, it is actually the b dot ds. I from 1 to infinity. So this is the line integral. Okay, so going back to here, originally I tell you that the direction of the loop can be determined by yourself, but here we will the direction will be determined by maybe you still can determine the direction by yourself, but it really needs to you somehow need to depend on the right hand rule. So now we have the loop like this. Maybe we have the loop like the orange one. And then as you can see here, we have I1 going out of the page, I2 going into the page, and then I3 going out of the page. So now we define the ampliance loop like this, counterclockwise. so that you use the right hand rule. You use a forefinger to follow the loop, and then the positive direction will be out of the page. So positive direction is out of the page, which is related to the definition of the loop. If the loop is counterclockwise, then the positive direction is out of the page. If the loop is clockwise, then the positive direction is into the page. Then, as you can see, I1 is enclosed by this loop. I1 is enclosed by this loop. So we will count I1 on the right side. We will count I1 on the right side. And it is out of the page, so it is positive. So we will count I1, positive I1 on the right side. And for I2, it is also enclosed by this loop. It is also enclosed by this loop. However, it is going into the page. So when we consider the I enclosed, it should be like I1 minus I2 to be I enclosed for this graph. And of course, I3 is not enclosed by this loop. It is out of this loop. So we don't really count I3 for this one if we define the Ampere's loop like this. So on the left side is just the integration. It's just the integration. And in this course, usually we'll give it as integrating over the uniform B field, or maybe it is like integrating the constant for a circle. So we will not make this integration too difficult. Usually hand calculation is good enough to work on this integration. But at least you need to define, you need to determine the I enclosed. Mu0 is a constant, so you don't need to consider about that. You just leave it there. So I enclosed, you need to determine carefully. So according to the direction of the loop, you can determine the positive direction, and then you count all the current enclosed by the loop. And then if it is the same as the positive direction, then it is positive. And it is opposite to the positive direction, then it is count negatively. So so the current I on the right side is the net current encircled by the loop. So here we know that if we use right hand rule to determine the positive direction, so here I1 is positive, I2 is negative. So it is a simple interpretation for the Ampere's law. So any questions? If no question,